Suppose I gave you the task to make up a new world. What would you do? A universe where experience is so vastly different than ours, it may as well be unrecognizable. What if I told you that you'd only have to slightly alter one fundamental thing, one small and simple rule, to transform reality as we know it? And what if I told you that such a universe would not be a black box, but that just from pure logical reasoning, just from pure thought alone about the world we live in, we can not only deduct but also simulate what it must be like to be part of it? This video will not only teach you the detailed steps required to get up to this point, it might also just show you a new way to think. A new way to think about how you live in and experience the world around you at such a simple and fundamental level that might just be able to open your eyes on something that your intuition alone has been hiding from you from the very moment you first opened your eyes. I am talking about the sheer beauty that is the fourth dimension. The sheer emergent beauty stemming from an unbelievably simple idea that has the potential to open up an endless realm of possibilities. Whether you have never heard about it, seen a confusingly transforming object, played a game that allows you to slice through a hyperdimensional world, or have a PhD in mathematics with specialization in geometry, I can almost guarantee you that this video will show you something you might not have thought about before. There are ideas that we'll get to in this video that I have not seen a single person bring up before. While it may be obvious that this video is not targeted towards a preschooler, I still want it to be understandable by anyone. This is why we are going to start from the very beginning, from the initial thought behind dimensionality and what it means in the first place. If you want to describe the position of an object, how might you do that? Well, the truth is that you cannot just attribute any object to some absolute position. It is only possible to describe the position and distance of an object relative to another. For instance, take this point in 3D space. Alone, this is not very useful, so let's turn it into a coordinate system. We will add an arbitrary line to it and call it the x-axis. While this line can be anywhere, the second line we will add has a constraint to it. It has to be in a 90-degree angle, in other words, perpendicular to our x-axis. We will call this second line our y-axis. This means that if we take another point and move it in the same direction as our x-axis, its position relative to the y-axis will not change. Right now, we have a two-dimensional system. If we have a point, we can describe its coordinates relative to our perpendicular axis using two numbers, which we will call x and y. So far so good. But we can do better. Let's add a third axis. It must be perpendicular to our other two, so since we live in 3D space, there's only two ways to define it. Let's define it like this. Now, if we take our point, we can describe its exact position relative to our three defined axes using three independent numbers labeled as x, y, and z. In other words, there are three different ways to move in, each with their respective reverse counterparts, which are right and left, up and down, and forwards and backwards. And all intermediate ways can be described as a combination of only these. A natural question might arise. Can we do better than this? What if we add another independent axis? Let's call it the w-axis. Mathematically, it's as easy as adding another independent number to describe position, meaning that any point in space can be described using x, y, z, and w. But what would that look like really? I mean, where do we put the fourth perpendicular axis? Should we put it here? Maybe here? Maybe is here better? Given the constraint that it must be in a 90-degree angle to all other three axes, this is fundamentally impossible in our universe, as our universe is primarily three-dimensional. So is this really it? Can we not add a fourth axis and see what it looks like? Well, most people talking about 4D space in a mathematical sense will say that yes, this is it. And I mean, in our physical universe it is. However, Despite common belief, our minds are capable of so much more. Even though I would love to, I could not just show you what 4 perpendicular axes look like. This is because I cannot even show you what 3 perpendicular axes look like. I mean, look at these 3 axes. They are perpendicular, right? Well, in 3D space they are. However, if you were to measure the angle between those 3 lines, you would see that none of them are actually 90 degrees. But we as 3D creatures accept them as being 90 degrees to each other anyways, because we know that we're actually looking at the projection of a 3-dimensional scene. This kind of backwards way of thinking about the world will be a common and important theme throughout the course of this video. We are so used to living in our 3D universe that we take our intuition for it for granted. Dropping this 3D intuition and seeing the world as it truly enters your eye is, in my opinion, the single crucial step towards developing a new intuition for 4D. You cannot comprehend 4D until you can fully understand how you are able to comprehend 3D in the first place. The 3D world we know and love is merely a mental map of what your senses tell you about your surroundings. And no, being able to judge how far away things are from each other is not the same as being able to truly see in 3D. The screen you are using to view this video is only able to display 2-dimensional pixels. Even the retinas of your eyes have light-sensitive cells arranged in a 2-dimensional pattern. Only a 4D creature would be able to truly see in 3D. But why and what would that look like? Let's talk about images. Let's consider a camera. A camera produces 2D images because it contains a 2D sensor. This 2D image is made of pixels, all of which are squares. Here, some pixels have been given a random color. When you take a picture, you can think of every one of these pixels as essentially looking into the 3rd dimension, in this case the z-axis. A 3D image would consist of cubic pixels arranged in a 3D grid. This is because each pixel must have unblocked access to the outside world. For a 2D grid with square pixels, every pixel can essentially look into the 3rd dimension. For a 3D grid of cubic pixels, however, all of the inside pixels are blocked by the ones on the outside. That is until we move up a dimension, which means to create another perpendicular axis to our existing 3. Now, every 3D pixel is able to look into this new W axis we have just created. Think of this as every single pixel shooting away into the perpendicular 4th dimension and seeing what color the first object that intersects with this ray has. This means that a 4D creature would have a 3D view of its world. Think of it like all the information of each cubic pixel being processed in their mind simultaneously. Another good way to think about this is to consider a creature living in 2D. It's only able to see a single dimension because a 2D retina here wouldn't make sense. If you consider a safe with an object inside, the 2D creature would have no way of knowing what's in the safe. We as 3D creatures, however, can not only see the safe and the object inside, we can see it in its entirety, including its walls and the inside of its object. This means that a 4D creature looking down on our 3D world could see it in its entirety. They would not only be able to see inside a locked up safe, they would be able to see everything, including the inside walls of the safe. The 3D retinas would be able to process an entire 3D image at once, which we are not able to do. Now, you might be wondering, how are we supposed to see 4D if we are not able to see a 3D image like a 4D creature would? Well, the answer is simple. We don't need to. Our brains are well adapted enough to understand 3D to the point where we can rotate or slice through a 3D image like this and build a mental map on how it looks in a 3-dimensional sense. Now that we have talked about how a 4D creature could see, let's talk about what a 4D creature might see. Arguably the simplest 3D object one can think of is the cube, which is a 3D platonic solid made of 6 square faces. But how do we construct a cube? Well, let's start with the simplest of cases, a 1D world with a single coordinate axis. You take a point, which you can think of as being a 0D object, duplicate it, move it along this one axis and connect the 2 points. If you want to create a square, you will need another dimension, the y dimension. Here, we will take our line from previously and we'll duplicate it, move this line up into the new dimension and connect the points. As you might be able to guess, we can repeat the same step again to create the cube. Just like previously, we will need a new axis to move in, the z-axis. We'll take our 2D square, duplicate it, and move this new square along the third dimension, and then once again connect all the points. But how do we go on from here? Sure, we can duplicate this cube without issue, but if you recall the steps we took previously, creating a 4D analogy of a 3D cube would mean moving the second cube along the fourth dimension. But where is this fourth axis? Where do we move this cube to? Well, if you recall what I said previously, you have to think about it in terms of projection. Even for the 3D example, we only got a 2D image. Look at the highlighted face of this 3D cube. Even though we understand that this shape is actually a square, projected to 2D it looks like a trapezoid or a parallelogram and not like a square. This means that while it is not possible to render a 4D object in full, it is absolutely possible to show a 3D projection of one. Let's take a closer look at our 3D to 2D case. We'll take a square, duplicate it and move it along the third dimension. If we look at this in the simplest case, which means looking at the cube straight on, it looks a little bit like a square inside a square, with each corner being connected by a straight line. Notice that there is one square that visually looks like it is smaller than the one encapsulating it. This comes from the basic fact that one is the front and the other is the back side, and that further away objects look smaller to us than those that are closer. This observation is an important one to make. If we consider the normal case of perspective projection, which is arguably the most natural way to perceive the world, an object that is further away in the direction we are looking in will look visually smaller to us than an object that is right in front of our eyes. It's no different in 4D. If we want to create the 4D analogy of a 3D cube, we might take this cube, duplicate it, and considering the simple case of looking at the hypercube straight on, moving it away in the fourth dimension looks like decreasing the size of the projected cube. Now we can connect the lines as previously. This inner cube, though it looks like it is inside the other one, is merely farther away from the camera, which makes it appear smaller, even though it is actually the exact same size as the larger looking one. We have created the 4-dimensional analogy of a 1D line, 2D square or 3D cube, a 4D hypercube, also known as a tesseract, which is a term coined by British mathematician Charles Howard Hinton in 1888 to describe a 4D cube. A tesseract has one cubic cell on the front and another on the back, and each square face of the front cube connects to a face of the back cube. This in turn creates 6 additional cubic cells to make a tesseract that is made of 8 equal cubic cells. Let's think about what would happen if we were to rotate this tesseract in the 4th dimension by first seeing what it looks like if a cube gets rotated in the 3rd dimension. We'll highlight the back side of this cube and start by rotating it by 45 degrees to the left. Now we are looking at an edge of the cube, however the highlighted side is still behind the center. Rotating it by 45 degrees again moves the highlighted side to the right side and makes it visually look like a trapezoid. Now we are bringing this side to the front by rotating it again. We now have a similar edge view as previously, just now with our side being in the front rather than the back. Our final rotation brings the side to the front. Visually, it now looks like this square encapsulates the entire object. Let's try the same with our tesseract. For clarity, I'll show the equivalent 3D rotation as we go. Here, I have highlighted the back cell of this cube, which looks like a small cube in the middle. Now, let's rotate this tesseract by 45 degrees so that we are looking at an edge. The highlighted cube seems to have moved to the side and became a little skewed. Notice the parallels to the 3D example, where the highlighted square seems to have moved to the right with a little bit of skewing outwards. Rotating it further, we get what looks like our original tesseract, but with one cell on the right highlighted instead of the cell in the middle. I want to emphasize that this is still the same side of the tesseract, and that even if it might not look like a cube, in 4D it really is a cube. Just like how a square has an area in 2D but is completely flat in 3D, a cube has a volume in 3D but is completely flat in 4D. So it's perfectly possible and logical to rotate it in a way that flattens it out. Anyways, a further rotation gives us the same skewed image as after our first rotation, but now with the entire right side of the object being magenta, as opposed to only parts of it. Before we complete our last rotation, I want you to take a quick moment to predict what's going to happen. Seriously, pause the video if you need to and think about what it's going to look like after I further rotate it by 45 degrees. If you're struggling to decide on an answer, take a look at the 3D video again. Quite anticlimactically, the square moves to the front and we get our square in a square from previously again, but now all in magenta. If you still got no clue, let me say the same thing as I just did, but instead of the word square, I'll use the word cube instead. The cube moves to the front and we get our cube in the cube from previously again, but now all in magenta. We have now done a 180-degree rotation on this tesseract. And now our highlighted cell is in the front, which is closer to us than all other sides and thus encapsulates the entire projected object. Just for fun, let's see it completing another half rotation until we're back to our original image. Also, note that while it might be difficult to intuitively understand how this is supposed to depict an object that's rotating, it only looks like that because we're not used to seeing four-dimensional objects rotate. However, if you were to look at it from a certain angle, you will notice that it actually does look an awful lot like its 3D counterpart performing a rotation. If you've already seen content talking about 4D, the things I've talked about so far might not have been anything new. However, we're now getting into the actual core idea that I want to talk about in this video, which is what it would be like to actually experience a four-dimensional world. I don't think that rotating hyperobjects or 3D cross-sections alone do the true emergent beauty of 4D justice. This is why arguably the most important thing to consider is how one would perceive a 4D world if one were to move and rotate around within it. Let's consider a 3D world with nothing but the wireframe of a cube in it. I light a static crosshair with the two viewport axes for clarity. Since in 3D there are 6 ways to move in, which are right, left, up, down and forwards and backwards, we will consider what happens to our rendered viewport when we move in these directions. Let's first move towards the right. This makes our rendered image move towards the left, where the back side of the cube seems to lag behind the front side because it is further away. Moving towards the left produces the opposite effect. The rendered cube moves towards the right in our viewport. A similar thing happens for up and down. The projected image looks like it moves in the opposite direction, with the smaller looking square seeming to lag behind the larger looking square, because this face is further away. But something different happens when we instead move forwards towards the cube. The projected image looks like it increases in size because we are getting closer towards it. On the contrary, moving backwards makes the projected image decrease in size since we're now further away. So far so good. Now let's move up a dimension. Recall from previously that we now need a 3-dimensional viewport instead of a 2-dimensional one. This means that our center crosshair now has another axis to it, the z-axis. We also have our tesseract from previously. The rules from previously still mostly apply. Moving to the right makes our projected tesseract move towards the left in our viewport, while moving towards the left makes it move towards the right, with the smaller looking cube, which is actually farther away in 4D, seeming to lag behind the larger looking cube. It's the same thing with upwards and downwards. The projected tesseract moves in the opposite direction that our camera moves in, with the side that is further away and thus looks smaller moving slower than the side that is closer and thus larger. If I move upwards here, notice how the projected tesseract it looks like it's going farther downwards. Well, if I move downwards, it is going farther upwards because I am moving downwards relative to it. However, since the z-axis is now part of our viewport, moving forwards and backwards produces a similar result to moving left, right, up and down. It moves the projection backwards if we move forwards, and forwards if we move backwards. So what's with moving towards and away from the object? This is where the new perpendicular w-axis comes in. We are looking into this w-axis, so if we move towards it, the projected image becomes larger. Or moving away from it decreases the size of the projected image because it is now further away from us in 4D. We can use the terms Anna and Kata, which are also coined by Charles Howard Hilton and are essentially the forwards and backwards of the fourth dimension, or essentially the towards and away of the w-axis to describe this movement. If you say that something moves towards Anna, it moves positively in the w-axis, and something moving towards Kata moves negatively in the w-axis. This is what I find particularly beautiful about 4D. Nearly everything we know and love about 3D is essentially the same in 4D, but with an additional axis and a 3-dimensional viewport instead of a 2-dimensional one. That just by moving in the directions, it's possible to position yourself so that this tesseract is anywhere within the viewport, and it's possible to move towards and away from it. Movement, however, is just one piece of the puzzle. The other piece is one that is seen by many as particularly intimidating and confusing, though it is just as beautiful. 4-dimensional rotation. In 3D, any rotation can be described using 3 separate angles. Commonly, this is thought of as rotation around the axis. Since there are 3 different axes in 3D, it's possible to rotate an object around the x-axis, the y-axis, and the z-axis. This is often also known as yaw, pitch, and roll. However, I won't be using these terms here, not only because I keep confusing them, but also because axis rotation is not a thing in 4D. This is because rotation is fundamentally a 2-dimensional operation. The x and y axis, for example, together span an entire plane of rotation, called the xy plane, where points can rotate within. This operation does not move a point outside of the plane, which in this case means that any point rotated in the xy plane does not move in the z-axis. In 3D, there are 3 planes of rotation, which are all possible binary combination of axes, which are xy, xz, and yz. The reason we often think about 3D rotations as being around axes instead of within planes is because 3D is the only dimension where there happens to be just as many planes of rotation as there are axes. This is why rotating in the xy plane is often described as rotating around the z-axis, rotating in xz around the y-axis, and rotating in yz around the x-axis. This idea of rotation around axes is fundamentally nonsensical in 4D because while there are 4 perpendicular axes, the addition of the w-axis adds 3 more possible planes of rotation next to the existing 3 xy, xz and yz planes, xw, yw, zw, which are all 3D axes combined with a new w-axis. Having 6 rotational planes as opposed to 3 might seem very intimidating at first. However, if we repeat the same steps as for movement, which is to look at the 3D example first and then try to extend that to 4D, it becomes mind-blowingly natural and intuitive. There's really just 2 ways to rotate in 3D first person, which is right and left and up and down. Imagine this rectangle as our camera. The 2D output from your mouse cursor corresponds to 2 of the 3 planes of rotation. Moving the mouse towards the right or left corresponds to rotation around the y-axis, or in other words, around the xz plane. For up and down, it corresponds to a rotation on the x-axis, which corresponds to the yz plane of rotation. If we go back to our 3D scene with the cube, if we rotate towards the right, just like moving towards the right, our projected image moves towards the left. However, the higher speed and without an increasing offset in the front and back sides like it was for movement. Rotating towards the left makes the image move towards the right. Rotating upwards makes it go downwards, and rotating downwards makes it go upwards. But wait, didn't we just previously say that there's 3 planes of rotation as opposed to 2? So where'd the third one go? Well, if we rotate our camera around the remaining XY plane, you'll notice that it just tilts the camera. This actually makes a lot of sense. Since we're looking into the Z-axis here, if we do not include the Z-axis into our rotation, then we do not actually rotate in any significant way. Here, the XY plane is the only plane of rotation where any point rotated within just rotates in the same plane that the camera exists in. So the XY rotation is generally ignored in nearly all first-person games. This generalizes beautifully to 4D. Since we're looking into the W dimension, that means that the only rotational planes that contain the W axis rotate in a useful way. Just like how in our 3D example, only the 2 axes that contain the Z variable we were looking into were useful, which were the XZ and YZ planes. Now, that only leaves the XW, YW and ZW planes. If you think back to our 4D movement example, recall that we were able to move the projected object anywhere to our 3D viewport, whether that is right, left, up, down or forwards and backwards. This means that rotating in the XW plane moves the projected image along the X viewport axis. This means that rotating in the XW plane moves the projected image along the X viewport axis in the opposite direction. In the YW plane along the Y-axis, and in the ZW plane along the Z-axis. Since the XY, XZ and YZ rotations all do not contain the W-axis, and we were using X, Y, Z in our viewport, rotating our camera along these planes just rotates every object within the viewport. In other words, XY, XZ and YZ are the 3 ways to tilt the 3D viewport in a 4-dimensional world, as opposed to the only one way of tilting the 2D viewport in a 3-dimensional world. This means that while a normal computer mouse with a 2D output is little to no use in a 4-dimensional system, adding just a single additional input axis makes complete 4D first-person rotation possible. The only other 3 of the 6 4D planes of rotation are merely camera tilt and can thus be ignored. So this is what 4D actually looks like. Not in the sense of seeing a slice of the world or shadows of single 4D objects, but what it would actually look like if one were to move and look around in a 4D scene. 4D is not as much as an unimaginable thing as many people claim it to be. Now don't see this as an attack on many truly awesome projects like 4D Toys or 4D Miner. The common slicing approach is indeed an easy one to get into if you want a playable, simple game in 4D, while rendering a true 4D scene using perspective projection might be a lot for 3D understanding brains to take in at first. But just like how a toddler can learn to walk, anyone can learn to get an intuition for a higher dimension. Now that I've explained the basics of a 4D world, I think a good next step would be to look at a few concrete simulations and examples to help build an intuition for 4D space. Here we are looking at a 4D scene. This 3-dimensional cube you see around everything is our viewport. In the center you can see our viewport axis. To the left you see I'm able to rotate the camera using certain sliders. For example, if I drag the XW slider towards the right, we rotate towards the right. Or if I drag the ZW slider to the left, we rotate backwards. Here is a wireframe of a tesseract, while the cyan tesseract is shown as solid. It's a similar story to the yellow cube you see here. It's a little bit cut off by the viewport, but you can still see part of it. It is also rendered in solid. However, I find the wireframe model in this case to be more understandable, which is why the vast majority of objects you will see in this demonstration are rendered using wireframe. It is also possible for me to move around with my keyboard. Now I'm moving towards the right. You see, the entire viewport looks like it moves towards the left. Now you might be wondering, what are these 2 objects you see here? Well, the bottom one is called a 5 cell and the top one is called a 16 cell. They are part of what can be thought of the four-dimensional analogies of the Platonic solids. However, we will learn more about those later on in the video. Let's rotate further towards the right to uncover more of the scene. Here, there's a green cube. This cube looks a little bit skewed, but it mostly just looks like a normal cube. I will align the crosshair so that it is inside the cube. Now, we are essentially looking at this cube. Holding the spacebar will move us towards the cube, while holding shift will move us away from the cube. In other words, space is Anna, while shift is Keta. Now we can do something interesting. What if we want to rotate around this cube? Well, what we can do is we can move towards the right, which makes our projected image move towards the left, right? Again, you have to remember that you have to look at it from this angle, because the x-axis is looking towards the right. Now, we can readjust by looking back at the cube. We can repeat this to essentially complete a rotation around this cube. And you will see, for one, we uncover more of our scene, because we're now rotating in the other way again. But for two, the cube now looks pretty flat. It previously was a completely solid cube with a normal 3D volume. And the thing is, it still is a normal 3D cube with a normal 3D volume. Just in 4D, we're looking at it in a way that flattens it out. Just like how we can look at a simple square, like a simple plane, from a certain angle and have it essentially appear flat, this cube appears flat. Let's uncover more of our scene. Rotate this way. Oh, here's an object. It's kind of at the top, so we will rotate towards the top. And it looks like we have two tesseracts here. The yellow tesseract is a normal tesseract. It's not that large. While next to it is not really a tesseract in the same way, because it has these scales. So it's differently scaled within the other dimension. Let us take a closer look at it. We'll once again align our camera so that we are essentially looking at this tesseract. And I will move towards it. And then I can do the same thing as previously. I can say rotate forwards, move backwards, rotate forwards, move backwards, rotate forwards, move backwards, and so on, right? And we can also do this with the x-axis, as we have seen. And with the y-axis as well. Now it kind of looks like the red tesseract has become really, really large, while the yellow tesseract is a little bit inside of the red tesseract. You can think of this as essentially being halfway inside of the red tesseract, while looking mostly at the yellow one. If we want to move towards the yellow one, we can hold space, and you will see we're essentially flying through the red tesseract. And only once we've completely flown through it, we arrive at the yellow tesseract. We can also fly through that one. Now, we can also turn around. Now, we not only see both tesseracts here, but also our existent scene. Now you will notice that it all looks a little bit tilted. So what I can do is I will use the camera tilt to tilt the camera back in a way that makes it all equal. We'll get to why this tilting occurs and what we can do about it later on in the video. Let's address the elephant in the room here. What is this weirdly transforming tesseract and that other colorful looking tesseract? Well, let's look at it and let's try to move towards it. Alright, so this lower tesseract is actually performing a rotation in the XW plane. These thin lines that look like they are coming from the center point are our actual 4D axis. If you've ever played Minecraft, this is a little bit similar to the 3D axis you see in the F3 menu, which kind of seem to statically stay pointing at the axis while you tilt around. If you look at the above object, it kind of looks like every actual axis points towards one of these outside cubes. This is because this cube doesn't actually have any rotation. It's completely aligned with our global axis. Only we are the ones that have rotated here. Here we have a different scene with a ground and a few objects. We can once again rotate towards the scene and move towards it in a similar sense. And you will see objects visually start to look like they kind of intersect themselves. If we rotate downwards and then move upwards, you will see that it kind of looks like the objects are inside of the ground. However, that's not actually the case. The objects are still in front. Remember, we should actually be seeing this entire viewport at once. However, we're only seeing a 2D projection of it. Let's rotate around further. I'm now using only my keyboard to both rotate and move around. Now you might notice that it all looks like it is a little bit tilted than before. This is an issue that we've had previously as well. And previously I had just readjusted it with the 3-dimensional tilt sliders. However, there's also another way, which is using absolute rotation. Now I have enabled absolute rotation. If you look at the sliders, you will notice that they do not jump back anymore. Because now I'm not continuously applying deltas anymore. And now the idea is that even though I might have moved around a lot, these 3 sliders alone still essentially describe my entire rotation. And I have not tilted in the 3D sense in any way, shape or form. This is actually what 3D games do. If we go back to our previous scene, and we rotate upwards, you will see there's a pretty interesting object here. And now if we tilt XW, it will just rotate everything in a specific way. It makes a lot more sense if we look at it from only one direction, ignoring the Z-axis. If we now rotate upwards, and now rotate towards the right, notice how it now looks like 3D. However, this way of rotating might be seen as a little bit more confusing because it's not quite as easy to look around initially. However, you can also get used to it fairly decently. You can kind of imagine it as describing a point in a 4-dimensional sphere. In our 3D example, the right and left and up and down rotations are a little bit like moving along the longitude and latitude of a wireframe of a sphere. In 4 dimensions, it's essentially the same thing. However, since our sphere is actually 4-dimensional, it has a 3-dimensional surface. You can kind of imagine it like a sphere being cut into infinitely thin slices. And now imagine each of these slices is another sphere, where you can use X and Y to describe the position again. However, the Z coordinate can essentially be thought of as describing which slice of this hypersphere to consider. If you've ever heard of the 3D platonic solids, then you'll know what makes them interesting. You take a bunch of the same 2D polygon and put them together in a way that creates an object that is face, edge and vertex transitive. In other words, an object that is pretty darn equal and symmetric. These platonic solids also exist in the 4th dimension, however they are not called platonic solids, but rather regular convex 4 polytopes, which is a little bit of a mouthful, but whatever. We already know one of these regular 4 convex polytopes, the tesseract, which is the 4-dimensional analogy of the cube. And just like how a cube is made of square faces, a tesseract is made of cubic cells, 8 of them to be precise. However, there's also other regular convex 4 polytopes. For example, what we have here, which you might call a 5-cell. 5-cell because it is made of 5 tetrahedral cells, just like how a tetrahedron is made of 4 triangular faces. This object can essentially be seen as the 4-dimensional analogy of the tetrahedron. Let's take a look what happens when we rotate it. Let's first rotate it in the XW dimension. It looks a little bit confusing from this perspective. So let us look at it from this perspective instead. And you see, now it actually looks a lot more than a 3D object that's rotating. Now we can also rotate it in the YW coordinate, still looks quite 3D. And ZW looks a little bit weird from this angle, because we are basically looking at the Z-axis right now. So let us rotate it in a way that brings the highlighted cell to the front. Since we want to bring it to the front, we have to rotate it forwards, and so we will increase the ZW slider. And you will see now, this cell is in the front. If you rotate it further in the ZW plane, you will see that at some point, the cell seems to become a little bit smaller. Every 3D platonic solid has a 4-dimensional analogy, which is, as we've already seen before, the cube has the tesseract, the tetrahedron has the 5-cell, but there are also others, like for example the 16-cell, which is the 4-dimensional analogy of the octahedron and is made of 16 tetrahedral cells, or the 120-cell, which is made of 120 dodecahedral cells and is essentially the 4-dimensional analogy of the dodecahedron, which, to be fair, looks like a monster, but what looks even more like a monster is the 600-cell, which is the 4-dimensional analogy of the icosahedron, which is made of 600 tetrahedral cells. And these are actually all the three-dimensional platonic solids. However, in 4D there's a little bit of a surprise, which is that there exists another regular four-dimensional polytope that does not have a clear three-dimensional analogy. It's the 24 cell, and it is made of 24 octahedral cells. And by the way, if you're wondering about higher dimensions, for 5 dimensions and up, the only regular polytopes that exist are the analogies for the cube, the tetrahedron, and the octahedron. In other words, the n-cube, n-simplex, and the n-orthoplex. Here we have what looks like a normal ordinary square. However, this square is actually a three-dimensional cube. If we look at it straight on, and I rotate YW and ZW, you will see how it looks a lot like a normal cube that's just rotating. Nothing special, it's a normal cube spinning around. However, it still looks flat. That's because a cube is infinitely flat in the fourth dimension. And if we want to create a tesseract, we can essentially just extrude this cube into the fourth dimension. Now by extruding it, every single face of the cube has been extruded to be turned into another cube. And so for the 6 faces of the cube, all of these 6 faces have been extruded into the fourth dimension to create new cubes. And if you add the 2 cubes on the side, the one we started with and the one on the other side here, then you get a total of 8 cells. And now we can rotate this tesseract around, and we can do the same extruding thing again, and we can see how we can take what looks like a squished cube and extrude it into the fourth dimension. I just think that this is a very helpful way to think about 4D, as cubes being essentially flat, however still 3D cubes. Even though it looks squished or here it looks completely flat, it's still actually a 3D cube, just infinitely thin in the fourth dimension. And so if I were to extrude it outwards, it actually has a 4D volume now. And we can still rotate it around in the same way, and it will always be an extruded cube. And now last but certainly not least, we have 3 tesseracts. Each of them is performing a rotation. The 2 magenta ones on the left are performing a simple 2-dimensional rotation like we're used to. However, the cyan tesseract on the right is performing what is known as a double rotation. Double rotations are actually exclusive to 4D, and they do not exist in 3 dimensions at all. This is because in 4D, it's actually possible to rotate in 2 completely different planes at the same time. Since we have x, y, z, w, an example of this is the first rotation being performed in the xy plane, and the second rotation being performed in the zw plane. And as we remembered, the point does not move in the other axis. And so rotating in the xy plane does not move the points in zw, so these 2 rotations can coexist simultaneously in 4D. This is what we see here. The bottom magenta tesseract is rotating in the xy plane, and the top magenta tesseract is rotating in the zw plane. If you look at it a little bit more closely, it looks like the bottom magenta tesseract is rotating normally, like you would expect a normal object to rotate. However, the top magenta tesseract seems to kind of transform in a weird way. This is because we're not looking into the W dimension. If we were to rotate a little bit and then readjust by moving back, so that we hide the x-axis and show the w-axis, it now looks like the other way around. Now this top magenta tesseract looks like it's performing a normal rotation like we're used to, while the one on the bottom looks like it transforms in a weird way. So it's really a matter of perspective. However, it's still just all rotating like normal, no matter how you look at it. In the double rotation, you can essentially think of this XY rotation on the bottom, which is like the normal rotation, which, it just looks like a normal rotation, plus this weird transforming looking rotation on the top being combined. And so it does the normal rotation, but it also does this transforming thing. This is essentially this double rotation. The simulation I've used here to visualize 4D is free and open source, and you can play around with it in the browser. See the link in the description if you'd like to check it out. However, note that as of right now it's still desktop only. However, it is made to be as usable as possible with only a single hand on the keyboard, as I've personally realized that it can often be rather difficult to understand depth within the viewport unless you can rotate it constantly. All of the relevant controls are listed on the website. However, the main important ones are WS for forwards and backwards, DA for right and left, EQ for up and down, and space for Anna and shift for Keta. The tab key lets you switch between using WASDQA for rotation or for movement. You can switch the scene using the drop-down in the top right corner. Now this is by far not a finished project, and there are countless of things I'm planning to do with it, so stay tuned. As a technical note, the project is made with Unity and is open source under the GPL 3.0 license in my GitHub, and you can find the link to it in the description as well. The code's definitely a little rough around the edges and currently lacks documentation, however feel free to contact me personally for any questions or other inquiries. Thank you so much for checking out this video. 4D is arguably my biggest interest ever, and I cannot wait for this video to be published and potentially show some people why it absolutely deserves that title for me. This video is a submission to 3 Blue 1 Brown's Year 4 of Summer of Math exposition, so if you enjoyed this video and feel like it gave you a glimpse into a completely new universe, consider registering as a Summer of Math Expedition 4 charge and voting for my submission once reviewing is open. Thank you so much for joining me on this. I hope this video at the very least gave you something to ponder on, and I wish you a great rest of your day. Goodbye.